Last time we have derived the central equation. This equation relates all the coefficients Ck that are separated by an inverse lattice vector to each other, forming a set of coupled algebraic equations. In this lecture, we consider the simple example of potential to clarify the importance of central equations. Now let us consider a simplest periodic potential as in cosine potential represented by u of x is equal to 2u0 cos 2 pi by ax. Consider only the nearest neighbor interactions u of x so that capital G is equal to small g or minus g at either side of k, where this small g denote the primitive inverse lattice vector, where capital G is equal to n times small g. So we can represent it as n into 2 pi by a. So the small g, the primitive lattice vector, inverse lattice vector is 2 pi by s. G is equal to 2 pi by a. Now we consider the Fourier component of potential u of x, that is ug and u minus g on either side, and we can represent these Fourier coefficients of potential on the same k-axis because that is also an inverse length, both are in the inverse length units. So this one we can represent it as 2u0 cos gs, that is u0 into e raised to igx plus e raised to minus igx. Equation from the central equation using the primitive lattice translation small g. The first equation represents the general wave equation we derived, that is h cross square k squared by 2m ck plus u ck minus g plus u ck plus g is equal to e ck. Now we have the minus g component, that is h cross square by 2m into k minus g all square into ck minus g plus u ck minus 2g plus u ck is equal to e ck minus g. Now the plus g component, that is h cross square into k plus g all square by 2m ck plus g plus u ck plus u ck plus 2g is equal to e ck plus g. Since this primitive lattice translation small g and potential u are knowns, once k is specified, then a set of coupled algebraic equations is completely determined. So actually there will be an infinite number of equations, but we will only consider a few equations in order to reduce the in order to solve these equations. Now the problem has been transformed from a differential operator as in the wave equation to a matrix operator eigen problems. So for a given wave vector k, the eigenvectors define the energy eigenfunctions while the eigenvalues are the corresponding energies. Then a block of determinant of the coefficients is given by from these three equations. This can be transformed into in the matrix format as you see here. So this is the matrix form, and the third row represents the first of the equations. You can just compare that. The third row is correspond to the first of the equation, and the second row corresponds to the second equation, and so on. Actually this is also there will be an infinite coefficient. There are many number of coefficients, so the full matrix will be an infinite one, but we in order to solve this one we truncated after 5 times. So we are only considering five rows in this, so the terms after this one will be truncated. At a given wave vector, each root E, or we can represent as Ek, lie on different energy band except in the case of coincidence. So the solution to above matrix gives a set of energy eigenvalues. We can represent it as Enk, where n is an index for the ordering the energies, and k is the wave vector that labels the ck, the coefficients ck. So in the next slide we'll see the energy bands, how the energy bands are created using this set of equations. The energy eigenfunctions have the following form, is represented by phi ke, that is equal to summation of g ck minus g e raised to ik minus gx, that is equal to e raised to ikx times summation g ck minus g e raised to minus igx. This is just a restatement of the Bloch's theorem, where these functions that is multiplied by e raised to ikx, that is summation g ck minus g e raised to minus igx, is a periodic function with period of the lattice. This reflects the fact that once a specific k is defined, all the coefficients correspond to that k can be generated, thus defining a solution labeled k. By considering the full matrix form, you can convince yourself that choosing two specific k's that are separated by any g would generate exact same matrix yielding identical solutions. That is, phi k plus g of x should be equal to phi k of x. This means that the eigenvectors and energy eigenvalues are periodic in G. So we can, in energy we can represent it as En k plus G is equal to En k. The energy eigenvalues can be obtained, we are considering the first within the first Brillouin zone, that is from minus pi by a to plus pi a by a. So you can see it in this figure. An order of solution is generated at each k point. These solutions are called the bands and labeled as for different indices n is equal to 1, 2, 3, etc. Thus one need to specify both k and label and the band index n to completely specify energy solutions. So for each k1, for specific values of k, there are different solutions. We can have, for index 1 we can have E1 k1, and for index 2 we can have E2 k1, and so on. For energy 3 it is E3 k1 and so on. So we have different energy levels, and that forms a band. So there is band 1, band 2, band 3, etc. So here we consider the simplest potential values, and we only consider a few terms. With that we can see that there are energy levels, and energy bands are created. So next in the next slide we will see the band gaps, the expression for band gaps. So that is also we are considering only specific points, that is at the zone boundary. At the zone boundary, that is at the edge of the Brillouin zone, that is defined by wave vector k is equal to plus or minus pi by a. We are considering the first Brillouin zone. So that is also equal to plus or minus half g, because g is 2 pi by a. We defined the permeability lattice translation unit vector as 2 pi by a. Again we consider the simplest cosine potential as we considered earlier, that is u of x is equal to 2u u0 cos gx, and the set of equations, the set of wave equation is the first one is h cross square k square by 2m minus e times ck plus u ck minus g plus u ck plus g is equal to 0. We consider we just rearrange this equation so that u ck minus g plus h cross square k squared by 2m minus e times ck plus u ck plus g is equal to 0, and the next term is we added with the k will be added with g, so that the next term will be u ck plus h cross square into k plus g all square by 2m minus e times ck plus g plus u ck plus 2g is equal to 0. So these are the two terms, first two terms. We just consider first two terms, and we can express in this in the matrix format. That is this will be h cross square k squared by 2m minus e u h cross square k plus g all square by 2m minus e times the column matrix ck plus g is equal to the column vector matrix 0 0. Now we substitute for k at the zone boundaries. First at k is equal to minus g by 2. So we just substitute for k here with minus g by 2. On substituting, you will get the corresponding to coefficient c minus g by 2 and c g by 2. And again we substitute for k is equal to plus g by 2. So you just substitute here with k is equal to plus g by 2. You will get another set of equations. So here this will be correspond to the coefficient cg by 2 and c3 by 2g. You just work out this one. The only way this homogeneous system of equation can have a non-zero solution corresponds to the determinant of the matrix has to be equal to 0. Then only we can have a non-zero solutions for the coefficients. So for the first two coefficients, that is c minus g by 2 and c plus g by 2, we can write in the determinant format, that is h cross square g by 2 whole square by 2m minus e u h cross square minus g by 2 whole square by 2m minus e in the determinant, that is equal to 0. So that the energy eigenvalues that we can represent it as, there are two values. The energy will be having one plus term and minus term, and the e plus or minus is equal to h cross square g by 2 whole square by 2m plus or minus u. Thus the energy has got two roots, one is E plus and E minus, and the separation between these two energy levels we can represent it as delta E, that is equal to E plus minus E minus, that is equal to 2 times U. Hence from this we can conclude that we are able to predict the existence of band gap, that is at the zone boundary there is a separation there is a separation between the energy levels, that is which is approximately proportional to the magnitude of the periodic potential. So this the central equations or the wave equation which is able to define the energy band gaps inside such material.